In this video, we discuss hypercubic networks. Hypercubic networks derive their name from the hypercube. In this video, we assume that you are already familiar with the hypercube and its close relative, the CCC. The hypercube and the CCC have four interesting properties. First, all the nodes in the network are homogeneous, which means that all nodes are alike and no node stands out. Second, each node has a short unique ID, usually about log n bits if there are n nodes in total. Third, each node has a small node degree, at most logarithmic in the number of nodes. Some networks have an even smaller node degree. The CCC, for instance, only has a constant node degree of 3. And finally, fourth, we want to quickly route from any node to any other node. In other words, the distance between any two nodes is at most logarithmic. If a network construction has these four properties, we call it a hypercubic network. In this video, we study some interesting hypercubic network constructions. Let's jump right in and start with n nodes. Where n is 2 to the power of d, for some arbitrary dimension d, in this example d is 3. We can uniquely name all these nodes with exactly d bits. First, we make d plus 1 copies of each node, like this. Now, in dimension 1, we connect the nodes in the top row to the nodes in the second row where the last bit is flipped, so we connect top row 0, 0, 0 with second row 0, 0, 1. And vice versa, like this. Actually, we do this for all the nodes in the top row. In other words, we connect all the top row nodes with their partners in the second row, such that their column names differ only in the last bit. In the second row, we add connections for the second dimension, so we connect node 0, 0, 0 with node 0, 1, 0, so with the node where the second last bit is different, also in the other direction, and also for all the nodes again. And in the third row we do the same thing again, but now for the third dimension, where the first bit is flipped, like this, again for all the nodes. We can name the individual nodes by column.row, so the top left node is called 0, 0, 0.1. This is known as a butterfly network. You need a lot of imagination to actually see a butterfly here. But you might be familiar with the butterfly topology from studying the fast Fourier transformation. The butterfly network is a famous hypercubic network, as it has all the good features that hypercubic networks need to have. Homogeneity, small node degrees and short routes. In fact, while they do look very different, the butterfly network is a close relative of the CCC. Just imagine merging each node on the bottom row with their partner on the top row. This way, all red paths form little cycles. It's still not quite the same as the CCC since the butterfly has diagonal edges. While the butterfly connects nodes on row I with nodes on row I plus 1, the CCC connects nodes on the same row. Let's change our viewpoint briefly. For this, let's flip the butterfly around. Now we remove some of the nodes, and most of the edges. If we do it like this, and we move the names down for better visibility, we eventually get another familiar structure. The balanced binary tree. A binary tree has roughly n nodes which can be named nicely. It has short paths between all the nodes, and every node has at most degree 3. But it's still not a hypercubic network. Only one hypercubic property is missing from the binary tree. The four properties are shown here for reference. Please pause the video and think which of the four is missing. The answer is that the binary tree is not homogeneous at all. The root of the binary tree is very different from all the leaves at the bottom. The root connects the left part with the right part of the binary tree. If we route from a random node to another random node, there is a 50% probability that this root would go through the root, so the root is a bottleneck in the binary tree. However, if we can afford it, we can buy a much more powerful machine and assign it the role of the root. We probably also would have to make the network connections to the root more powerful to handle the additional traffic we might expect near the root. To a lesser degree also the next layer, the nodes next to the root, will see more traffic. So let's also make these nodes and edges somewhat beefier. If we do all this, we get what is known as a fat tree. A fat tree is not really a hypercubic network because we need to buy more powerful nodes and edges to make it work. Alternatively, we do not need to buy a bigger machine for the root. Instead, we simply have many normal machines which share the load of the root, and the same also for the second layer, like this. And now we connect these machines to the machines on the next layer. If we do this in a systematic way, we end up with the butterfly again. So the butterfly is really just a distributed fat tree. Maybe this is a good time for a little summary. We now know various network architectures: hypercube, cube-connected cycles, and the butterfly network. We can see here that all these networks have similar properties regarding node degree and network diameter. The hypercube is a bit worse regarding node degree, but it has the advantage that there are many more alternative paths between any two nodes. We also talked about the binary tree and the fat tree. Even though their numbers are similar, they are not hypercubic networks because the root plays a special role in both networks, and hence the nodes are not homogeneous. Let's try one more vantage point. This time, we start with a linked list, the simplest connected network. Is the list a hypercubic network? Please pause the video to figure out the answer. Well, a list is pretty homogeneous, rootable, and the nodes have at most degree 2. The only problem is the large distance between nodes, which grows linearly with the number of nodes. So if a list has n nodes, the distance between the two nodes on the left and right end is n-1. If we want to break this long distance, we might consider a two-dimensional structure, also known as grid or mesh. Now if we have n nodes, the distance between any two nodes already shrinks to 2 times the square root of n. If we add more and more dimensions, the size of each dimension shrinks every time. How does this end? Please pause the video one more time. Every time we add another dimension, the number of nodes in each dimension becomes smaller. From n with the list, to square root of n with the grid, to n to the power of 1/3 in the third dimension. Eventually we only have 2 nodes in each dimension, but we have logarithmically many dimensions. And what is this called? Yes, exactly, this log-dimensional structure is exactly a hypercube again. Let's go back to our summary table and add the 4 new topologies at the bottom. As mentioned, the first 3 are not really hypercubic since their diameter is too large. But adding more and more dimensions brings us back to the original hypercube. Next, let's study some really interesting hypercubic constructions. We start with the shuffle exchange network. Let's first explain the rules of the network with a single node, say the node with ID 010. The ID of that node has 3 bits, so we have a network in dimension 3. We add an edge from node 010 to node 011 just because that node has the same ID with the last bit flipped. Exchanging that last bit is called an exchange. We also need a shuffle step where we move the last bit of an ID to the front. Likewise, we also move the first bit to the end. These are called shuffle edges. Also, the nodes 001 and 1010 are connected by such a shuffle step. We simply move the first bit of the ID to the last position or vice versa. We can also shuffle the 3 bits of 011 and get an edge to ID 101, respectively 110. By moving the first bit of 110 to the end, we get to 101. Only 2 3-bit strings are missing in our picture. We can get to 000 by exchanging the last bit of 001, and likewise, we can also get to 111. Note that 000 does not have any shuffle neighbors. If we shuffle 000, then we just arrive at 000 again. If we add the missing exchange between the 2 nodes on the top, our network is complete. Because of the 2 operations shuffle and exchange, this network is known as the shuffle exchange network. The shuffle exchange network has some good properties. We have n nodes with label size log n, and the degree of each node is at most 3, because each node has exactly 1 exchange neighbor, and at most 2 shuffle neighbors by moving either the first or the last bit to the other side. Also, the distance between any 2 nodes is small, since with 1 exchange followed by 1 shuffle, we can fix 1 bit at the time until we are at the destination. Our final example of a hypercubic network is the Bruijn graph. The Bruijn graph essentially combines the shuffle and exchange steps into a single operation. In this operation, we take the ID of a node, in our example 110, and we remove the last bit. Instead, we add a new bit 0 at the beginning, so 110 is connected to 011. However, instead of adding a 0 at the beginning, we could also add a 1, so 110 is also connected to 111. Because of symmetry, we could also remove the first bit and then add a 0 at the end, or add a 1 at the end. This gives us all the 4 neighbor nodes of node 110. If we do the same for all the other nodes, we end up with the complete De Bruijn graph. While this graph has node degree 4, the distance is at most log n, since we combined the 2 shuffle exchange steps into a single step. This completes our small tour de force on hypercubic networks. As a summary, let's again see all hypercubic networks we have discussed in this video, together with their properties. We added one more hypercubic network at the end, which is known as the pancake graph. It manages to bring down the diameter such that it matches the degree. If we want to minimize the maximum of degree and diameter, the pancake graph is a really nice solution. The pancake graph is also interesting because it has been suggested by 2 famous people. The second author is one of the most prolific computer scientists in the world, Christos Papadimitriou. The first author is a young Bill Gates, some years before he dropped out of Harvard and co-founded Microsoft. Thanks for watching this video.